Great, you're still with me. The third problem I will present reveals a third limitation in my thought processes and stimulates a search for a third tool to overcome it. The description is a little longer, but it is very important in understanding why the Benny decision, normal procreative behavior, leads to ever-increasing conflict. The automobile crash problem, to which I refer, does not exist today. But it did exist before cars had seat belts and before federal safety standards forced us to seat belt our kids in the back seat. Imagine yourself driving down a road about 30 miles an hour. Your unbelted child is seated beside you. A big truck blocks the road and there's no way around it. What do? You slam on the brakes and you put your arm out to keep your child from flying into the dashboard. I'm sorry to inform you, putting your arm out to hold your child back did not reduce the child's injuries. People who did it increased the injuries of millions of children. And they killed hundreds of thousands. That is, hundreds of thousands of children would not have died if their parents had kept their arms down. If this car crash problem was so easy to understand, all the people who raised their arms over that 75-year period would not have done it. Let me see if I can explain what happened to derail people's thought process. We will need to look closely at the movement of people inside cars and the impacts that injured them. The dynamics are complicated. We will need a helper problem to make them simple. By helper problem, I mean something like the matchmaker problem, which helped us understand the mutilated checkerboard problem. Let me present the balcony problem to help make the car crash. Let me present the balcony problem to help make the car crash dynamics easier to understand. You're standing on a balcony, 3 floors up. Behind you in the apartment is a raging fire and you have to jump. Below is a concrete parking lot. I picked a 3rd floor balcony because after falling 3 floors, your speed will be about 30 miles an hour. Someone puts out a 1-inch foam pad to cushion your fall. Then someone else puts out a 12-inch foam pad. On which pad do you want to land? Everyone picks the 12-inch pad. Now let me describe the auto crash problem in a way that will allow you to see how the 12-inch and 1-inch stopping distance fits into the decision to put your arm out. When a car crashes into the big truck, the front end crushes 12 inches. Everything behind the wrinkled part of the car stops in 12 inches. For example, the rear bumper stops at 12 inches. The seat stops in 12 inches. The dashboard stops in 12 inches. And if you're seat belted, you stop at 12 inches. Your head does not hit the windshield because the windshield moves 12 inches forward at the same time. The belt loads are 20 times your body weight, or about 3,000 pounds. Inside your stomach, a steak feels like a bowling ball. However, because car crashes are so short in duration, about the duration of the pop you hear when you snap your fingers, the 20G stopping experience causes no serious injury. People walk away with only bruises. Let me give you another example of crashing with no serious injury. If you happen to be leaning down to pick up something on the floor. That is, your head and knees are up against the dash when the car hits the truck. You also stop in 12 inches. The forces on you are the same magnitude as if you're wearing a seat belt, and you walk away from the accident with minor injuries. Now you know 12-inch stopping distances produce low forces and low injuries. Next, I will show why not holding back a child results in a 12-inch stopping distance and minor injuries, while holding back a child results in a 1-inch stopping distance and fatal injuries. There are two parts to slowing down a car in an accident. The first is the slowing down during braking, which amounts to about a mile an hour. And the second, which is slowing down after hitting the truck, which in this case is 30 miles an hour. Holding back a 40-pound child during braking requires a 20-pound force, a force most people can create. However, when the car hits the truck, it slows down 40 times faster than when slamming on the brakes, and the force required to hold the child back is 40 times bigger, or 800 pounds, and no one can keep the child on the seat during a crash. Assume you did hold the child back during braking. Then the child would be on the seat in this position when the car hits the truck. Because you can't hold the child back anymore, the child would continue forward at 30 miles an hour, while the dashboard would rapidly slow down. After 6 of the 12 inches of car crush were completed, these parts of the car would be slowed to 15 miles an hour, and the child is still going 30 miles an hour. After the car is crushed a full 12 inches, these parts of the car have now stopped. The child's head is still going 30 miles an hour, and it slams into a standing still dash panel. The head makes a 1-inch dent in the dash panel. The child's head has to slow down from 30 miles an hour to 0 miles an hour in 1 inch. Same as jumping off the balcony onto the 1-inch pad. Now let's look at what happens in the case where you don't put your arm out. Assume this car is traveling 31 miles per hour. As before, you slam on the brakes before the car reaches the truck. The car slows down from 31 to 30 miles per hour. Because your arm is down, the child keeps going at 31. That is, the child is moving toward the dashboard at 1 mile an hour. Now, before the car gets into the truck, the child catches up with the dash. There's a 1 mile per hour collision. The child gets a bruise from banging into the dashboard at 1 mile an hour. Now the child and the dash are both going 30 miles an hour when they collectively crash into the truck. After the first 6 inches of the car crush are completed and 6 inches are remaining, both the car and the child have reduced speed to 15 miles an hour. After 12 inches of crush, both the child and the car are at rest, and the forces on the child, who stopped in 12 inches, are the same, relatively, as the forces on the seat-belted passenger who stopped in 12 inches. The child walks away, bruised, shaken, but not seriously injured. I did not drag you through this complex proof to teach you to keep your arms down to protect your children. That would have been a waste of time. Seatbelts protect your children. I did it to get you to think about how you gather, process, and value information. That on the balcony, you did these 3 tasks confidently and got a good result. In the car, you did them equally confidently and you got a bad result. In this next section, I want to explain why. The explanation includes a description of a third weakness in my thought process. To implement this description, I will use the relationships between stopping distance and stopping force. People correctly understand part of this relationship as they demonstrated by the behavior chosen in the balcony problem. However, part of this relationship remains hidden, as demonstrated by the behaviors chosen in the seatbelt wearing and putting your arm out problems. Let me take a closer look at how these two variables that make up an important portion of our daily lives are related. Think of a car. It has a coffee cup on the dashboard, and it is traveling 30 miles an hour. Take your foot off the gas and let the car coast 400 feet to a stop. The force in the coffee cup is so small it does not move or spill. If we had to give that force a number, it would be 0.05 G. If we brake the car to a normal stop, the stopping distance is 200 feet. The force on the cup is still quite low. The coffee still does not spill. To give this stopping force a number, consider 0.1 G. Now, if we slam on the brakes and the car comes to a halt in 40 feet, the coffee spills. The force on the cup is 0.5 Gs. Now look at the three stopping distances and three stopping forces. As the stopping distance shortens, the stopping forces increase. That's why when we jumped off the balcony, we picked the thicker pad. However, there is a hidden part of the relationship that is not so obvious. Notice that when the stopping distance was shortened 200 feet, the stopping force doubled. Therefore, when the stopping distance was shortened a lesser amount, 160 feet, we might predict the increase in stopping force would be less than 2 times. However, this prediction would have been incorrect. The actual stopping force increased 5 times. When we realize that the linear relationship we expected to exist between stopping force and stopping distance does not exist, we begin to understand the meaning of the nonlinear relationship that does. We begin to understand why we have been making some incorrect predictions and choosing some less than perfect behaviors. To more fully understand what nonlinearity means, let me make a table of the information we have thus far created. I will put the stopping distances that we have visited in the last 10 slides here, and their related stopping forces here. Remember that each entry in the table is for an object stopping from a speed of 30 miles per hour. For example, coasting to a stop. Stopping distance 400 feet. Stopping force 0.05 Gs. Normal braking, stopping distance 200 feet, stopping force 0.1 G. Emergency braking, stopping distance 40 feet, stopping distance 0.5 Gs. Now I'm going to introduce something new, a sport car braking. And we haven't discussed it before, but inserting it now will help our understanding. It has a stopping distance of 20 feet and a stopping force of 1 G. Crashing with seatbelts. Stopping distance 1 foot, stopping force 20 Gs. Crashing without seat belts, for example, the child's head stopping in just the instrument panel crush, stopping distance, let's call it 1/10 of a foot instead of an inch, and stopping distance 200 Gs. Next, I want to plot these numbers on a graph. Stopping distance on the horizontal axis, stopping force in Gs on the vertical axis. The coasting to a stop distance lies at 400 feet, but that's off the page to the right, and it's very close to the 0 G line. The normal braking stopping distance 200 feet and stopping force very close to the 0 G line. Emergency braking stopping distance 40 feet, still close to the G line. Sport car braking stopping distance 20 feet, stopping force 1 G. Crashing with seatbelt stopping distance 1 foot, stopping force 20 Gs. And finally, stopping distance for crashing with seat belts, head hitting the standing still dash panel, 1/10 of a foot stopping distance, stopping force 200 Gs. Plotting the table's points reveals some relationships between stopping distance and stopping force. Most obvious is that most of the points lie along two straight lines, one near horizontal and one near vertical. However, something can be learned about weaknesses in my thought process when we realize the points that lie along the x-axis, those from the blue highlighted area, are part of most drivers' braking experience. When we use this experience to predict the forces related to the shorter but not experienced stopping distance, we expect these forces will increase but will remain near the x-axis. For example, we correctly predict by linear extrapolation slightly higher stopping forces for sports cars with better brakes. We correctly believe that the coffee will tip faster and splash more. However, our experience in the blue part of the curve does not extrapolate to, does not predict the abrupt increases in stopping force of these points. Why should it? In the range of our experience, the yellow area in the table, we have shortened the stopping distance almost 400 feet, and the stopping force has increased less than 1 G. Why should we believe that a few more feet of shortening will radically increase the stopping force? Nothing in the blue section will tell us that shortening the stopping distance into the red section will increase the stopping force factors of 100. So now we know why people put their arms out to hold their children back. They were not worried about making a short stopping distance for their child. Short stopping distances have no significant meaning. Why should they be discovered and avoided? Parents have no motivation to check to see if putting an arm out, besides preventing a bump into the dashboard, somehow can create a short stopping distance and great injury. With the help of this guided tour, we have discovered the nonlinearity between stopping distance and stopping force. However, we might ask, was creating this understanding of the nonlinear relationship between stopping distance and stopping force an impossible task for our parents? Is it an impossible task for us today? How could our parents have predicted, how could we have predicted the huge stopping forces that result from a holdback behavior? Is there a simple relationship that connects each of these stopping distances to each of these stopping forces. For the 30-mile-an-hour stopping speed, can dividing some number by any stopping distance in feet provide the stopping force in G's. It looks like 20 works for that number. Check the table. What do you see? The number 20 divided by a stopping distance 20 feet gives the correct stopping force 1G. The number 20 divided by a stopping distance of 40 feet correctly produces 0.5G stopping force. A person using this equation can predict the stopping forces for any stopping distance. Direct experience is no longer required. For example, we can calculate the stopping force for jumping off the balcony into a swimming pool that stops our fall after we penetrate the water 5 feet. It will be a point inside this circle. Let me expand the circle so you can see more clearly. The water stops our fall after we penetrate a 5-foot distance. We can calculate the stopping force. It is 20 divided by 5, or 4 G's. 4 G's stopping force, 5 feet stopping distance, places a calculated point into the graph that appears to be along its smooth curve. It appears this equation could give corrective forces for any stopping distance. We now have enough information to describe a third weakness in my thought process. It is the non-recognition of 3 things. I don't recognize nonlinear systems within which I am immersed. 2, I don't recognize when my experience does not extrapolate. And 3, I don't recognize my behavior's effects on the motions of a nonlinear system. When I jumped off the balcony onto the thicker pad, I was using linear extrapolation of my experience. It was just luck that the thick pad was thick enough. If the choice had been between a 1-inch pad and a 2-inch pad, I would have picked the 2-inch pad, and the resulting much higher forces would have killed me. The deadly meaning of a willingness to extrapolate linearly from direct experience in systems that are nonlinear becomes fully apparent when we realize how it helped people not wear seatbelts in 1968, and how it helped us to this day put our arms out to protect our children in a crash. Let me repeat this argument graphically. Some dynamic systems are described by a smooth line with a sharp bend. For most of the horizontal axis, the line rises very slowly, and then for some small values of x, the curve rises steeply. We define this kind of system as nonlinear. That is, not a straight line. Our less than optimal behaviors are based on our experience with the blue everyday operating portion of the system, which seldom predicts the unpleasant events in the red portion where we have no experience. Since all the points in the line are predicted by a single equation, and that equation can be derived from information in the blue portion, that is, our everyday experience, we have a process that can predict the values of the curve in the yellow region where we have no experience. It is the motivation and capacity to abstract, that is, to build the equation, that allows us to pick the appropriate behaviors for events we have not experienced. We now have enough pieces to describe a tool to overcome my third thought process limitation. I call the tool abstracting nonlinearity. Abstracting nonlinearity contains 3 steps. The first step, if I participate in an environment like driving a car, I have to check to see if the car road system contains nonlinear relationships. For example, I have to look and discover the surprising relationship between stopping force and stopping distance. It may be hidden from my simple experience, but not from a how things work analysis. It may be hidden from a simple experience, but not from a how things work analysis. The second step, when I do find nonlinear relationships lurking in my system, I then know to distrust my experience for guidance in selecting safe behavior. Step 3. Find and use a how things work analysis rather than linear extrapolation of my experience to extend relationships between variables into regions I have not experienced. This is extremely important for nonlinear relationships because my experience linear extrapolates to this straight line and not to the points that describe the real system. You have now completed most of the hard work to understand 3 limitations in my thought processes. Limitations that I share with billions of people who are about to make Benny decisions. The first, there are too many elements in my system for my abilities to integrate them into one manageable conception. Their magnitude prevents me from correctly predicting outcomes of alternative behaviors. The second is, system elements are all changing at the same time. This prevents me from seeing how one element's change is affecting change in another. The third is, some of these elements are changing nonlinearly. That is, my experience of an element's change, my samples of that element's past changes, will not, using linear extrapolation, help me predict the element's future values. I have shown you 3 tools to help overcome these limitations. The first was coupling. Coupling connects several seemingly independent elements into groups which themselves have relationships that help create an understanding of the system. The second was simultaneity. Simultaneity reveals a consistent relationship between 2 variables that appear to be changing independently of one another. And the third is abstracting nonlinearity. That is, when you abstract your experience rather than use it directly to make predictions. In the next portion of the talk, I will apply these tools to the Benny decision, the decision to have a second child. If you don't mind, to take the heat off myself and Benny, I will use a more neutral question as I proceed forward. How many children per family lead to peace? Using limited thought processes, our predecessors and most of us have already answered this question and chosen the number of our children. However, if we now ask the question again, and this time apply the corrective tools, we should be able to see, maybe for the first time, which numbers of children induce ever-increasing peace and which numbers induce ever-increasing conflict.